Sound check one. Sound check two. Good morning. We're going to get started shortly. If you have any questions, you can type them into the chat bar. Remember to type your name or alias and your course, which should be Mac 1311, into the chat bar to get your bonus points. Okay, so for students who are in my Mac 1311 class, I just want to show you that if you go to the Canvas classroom and you scroll down to on the home page of our classroom, scroll down to notes, excuse me, notes and live chats, there is a link. Let me make it a little bit bigger here so you can see it better. There's a link that says OneNote folder. It says your instructor has set up a OneNote folder for this course. Any lecture notes from live chats will be posted in this file. So that's where I'm going to be writing what I'm writing today in the live chat. Welcome, Trina. Thank you for being here. So if you want, you can pull that file up on your computer at home. And if you go to the live chats, actually let me show you what it looks like when you click on it. So I'm going to click on the OneNote folder. Okay, let's see. I need to refresh it. Huh. Oh, there we go. All right, so here's the live. You have to, I guess, click the menu up here, the notebook list, and click on live chats. And you'll see the document that I'm going to be working on, which is just a printout of our practice test 1 from my math lab. And at any time, you'll be able to come back to this and see what I've written, see the document, but also right now, if you want to scroll through the document at home and check to see if there's particular questions that you would like me to work, you can always let me know by typing that request into the chat bar. Okay. All right, so let's go back to my version here. And until I receive requests, I am going to pick certain examples and work those. So, by the way, there's a little bit of a delay between when I speak and when you hear me, and possibly when you type and I can see it. So just be patient, and I will see your question or comment in the chat bar. Okay. Right now, if you would, Trina, can you let me know if you can hear me? By typing yes into the chat bar. Oh, fantastic. Okay, good morning. All right, so I'm going to start by working item number 2. So item number 2 asks us to find a limit. And it's important to realize that finding a limit often, not always, but often just comes down to plugging in a value. And the reason for that is we know that the limit is going to just be the function value under certain circumstances, particularly where the function is continuous and defined. So what we're going to do here is we're going to observe that the limit of a square root is just the square root of the limit as long as we get a positive value. Ooh, my writing's a little stretched out there. Let's see. Let me move my tablet around a little bit. Okay. Okay, so in other words, you can plug in as long as you're going to get a positive value under the radical, because that's where square roots are continuous, is where we are taking the square root of a positive number, or 0. So the limit as x approaches -9, well, I said or 0, but that's coming in from the right, from the positive direction. But anyway, we're not headed toward 0 here, because if you look, if we plug in, and this is a linear function, it's continuous everywhere. If we plug in -9 into that, we're going to get the square root of 8 times -9 plus 75. And then that's going to be the square root of -72 plus 75, which is a positive value. So this is going to be the square root of 3, which is why they say the answer here is D. Okay, so just keep in mind that pretty much as long as you plug in and get a real number, you don't get undefined, you don't get an imaginary number, that you can calculate your limits just by plugging in. Okay, now let's see. I'm going to scroll down a bit. Okay, solving exponential equations using logarithms is a skill folks often forget from pre-calculus. So let's go over item number 5 now. So there are basically 2 approaches to solving exponential equations. One, we can rewrite both sides as a power of the same base. But unfortunately, the number 28 is not a power of 2, right? The powers of 2 are, let's see, 2 squared, which is 4, 2 cubed, which is 8, 2 to the 4th, which is 16, 2 to the 5th, which is 32. And you can see we skipped right over 28. So this is not a power of 2. So we can't write this as, say, 2 to the 5th power on the right. So instead, we're going to use logarithms, and most commonly natural logs. And there's a couple of different ways to go about it, but I think the way most people like the best is to just take the natural log of both sides. So why would that be helpful? Well, there's a rule of logarithms, or a property of logarithms, that says that if you take the natural log of 2 to a power, you can bring instead the power out front and multiply by that power. So this left side turns into x times the natural log of 2 according to the power rule. And then we have still natural log of 28 on the other side. To get x by itself, then we're going to divide by natural log of 2. It's going to give us natural log of 28 over natural log of 2. Okay, now that was using the power rule. Sometimes there's some other rules that make simplification possible, but you have to be careful because people get them confused. So I just want to mention, you probably know that there's a quotient rule for logs, and you might think, oh, that might be something we can use here because we have a quotient of logs, but that's not true. What the quotient rule of log says is that if you have the log of a quotient, then that's the difference of the logs. So Notice that here we don't have the quotient inside of a single log. We have a quotient of two separate logs. So this rule does not apply there. There's nothing we can do. We can't subtract 28 minus 2 or divide 2 into 28 or anything like that. So you just have to leave your answer in that form, and it will look like this. Okay. If you have any questions about any item that I'm working, you can type it into the chat bar, or even if you just want me to repeat something, let me know. Also remember that you can go to your OneNote file and you can look through the document that I'm looking at, and you can see if there's any particular items that you'd like me to work. But right now I'm going to move on to another question. Just because I'm skipping a question doesn't mean it's not important, but I just want to hit some of the highlights here. Alright, so one type of problem that people forget from trigonometry would be something like this. So it says draw a right triangle to simplify the given expression, and we have the sine of an inverse cosine of x over 2. Alright, so just some basic reminders from Trig. The sine of an angle theta is the opposite over the hypotenuse. The cosine of an angle theta is the adjacent over the hypotenuse. And the tangent of an angle theta is opposite over adjacent, or in other words, the sine divided by the cosine. Alright, when we talk about the inverse, instead of the argument being the angle, the argument is the ratio of the sides, and the output is the angle. So this value inside the parentheses, inverse cosine of x over 2, this is actually an angle. So I'm going to give it the name, let's do alpha. So let's call this angle alpha here. So alpha, I'm just using alpha to, be able to discuss with you the properties of the inverse cosine. You could use any symbol for the angle. But what this means is that if we took the cosine of alpha, that we would get x over 2. And they're telling us to use a right triangle to analyze this situation. Notice that if this is alpha inside the parentheses, then what we're really trying to find is the sine of alpha. So we're looking for sine of alpha. So we're going to draw a picture with what we know. What we know is that the cosine of alpha is x over 2, and what we're looking for is the sine of alpha. So I'm going to draw a right triangle. And let's suppose that this is the angle alpha that we're looking for, or we're looking for the sine of, rather. Then we know the cosine is the adjacent over the hypotenuse. So it's possible that this side, the adjacent side to the angle, could be x, and the hypotenuse could be 2, and that would be consistent with the cosine of alpha being x over 2. And then what could we use to get the third side? Well, we know the relationship between the lengths of sides of a right triangle is given by the Pythagorean theorem, a squared plus b squared equals c squared. And so what we would have here is our legs are x and the unknown side, and the hypotenuse is 2. So we would know that x squared plus the unknown side squared is equal to 2 squared. So the unknown side squared is going to be 2 squared minus x squared, or 4 minus x squared. Let's just go ahead and make that a 4. Okay. So that unknown side then is going to be, if we're working in a right triangle, this side can be only a positive. So that would mean that we're only looking at our unknown side being the positive square root of 4 minus x squared. So what would the sign of alpha be then? So sine, remember, is opposite over hypotenuse, and we just found that the side opposite alpha is square root of 4 minus x squared. So that would mean that the sine of alpha would be the square root of 4 minus x squared, the opposite side, over the hypotenuse, which is 2. So that's where they got their answer there. Okay. All right, so I think the key here is just to remember that when you take the inverse trig function of some expression, what you're finding is an angle, and to give that angle a name, and then you can work from there. Okay, if you're watching the recorded version of this, if I go too fast, you can always rewind. And you can always post comments on the recorded version as well. All right, let's go ahead and look at some more. Okay, so let's talk about limits using a graph. Oops, pushed the wrong button here. Okay. So limits are probably a new concept for most people taking Calculus 1. So it's important to understand what we're referring to when we talk about a limit. So in algebra, we talk about function values, what happens at a particular value. For example, in part A here, it says find f of 2. And so if you look at the graph here, trying to find f of 2, what does that really mean? It really just means that you're saying when x is equal to 2, what is the y value? So you come over to the graph and you find the x value 2. This open dot is not a point on the graph, right? That's showing that there's a gap there. The actual function value for the x value 2 is the y value corresponding to this dark point here, so that's 5. So f of 2 is equal to 5 would be the answer to part A. Okay, the reason why we always like to ask you about the function value is because the limit may or may not equal the function value. And so people need to get used to that idea that the limit is the y value that the function was approaching very close, if you're very close to 2, but it's not actually the function value at 2 necessarily. So I'm going to erase what I drew on here. So now if I ask you for this guy, the limit as x approaches 2 from the left, that little minus means from the left, then if you look at your graph, you're not looking at actually what happens at 2 like we did a minute ago. Instead, we're looking at what happens when you come in toward 2 from the left. So imagine your finger following along the graph on the left side of the value 2. Follow along the graph, and you're asking what is it headed towards. So it's headed towards this open dot, which actually has a y value of 4. So the answer here would be that the limit as x approaches 2 from the left is 4. And sometimes the limit from the left is different from the limit from the right, but in this case, coming in from the right towards 2, we're actually headed towards that same open dot. Now notice I'm not going way out here when I'm talking about 2. With limits, you're looking very, very close as you want to the value that was given. In this case, we're looking at 2 because we're looking at the limit as x approaches 2 from the right. And so we're following along the graph, coming in closer and closer to that same point. So the value of the limit there is also going to be 4. These are called one-sided limits when we talk about the limit from the left or the limit from the right. But we also have the overall limit. So the overall limit, the limit as x approaches 2, is a combination of the limit from the left and the limit from the right. So if it just so happens that from both the right and the left, you're headed towards the same point, which is the case here. Then you say that the limit exists and is equal to that value, in this case 4. But if the graph had been headed towards different values from the left and the right, then the limit would not exist overall. All right. Oops, sorry about that. All right, so in this case, since it was 4 from the left and 4 from the right, it's 4 overall. Okay, so the next thing that we're going to look at is it's the same graph, but we're going to answer some other questions about when x is 4 or near 4. So x being 4, not y this time. So the first question, actually, I think I want to copy this graph if I can. Let me see here. Let's see if we can give this a shot. There we go. Okay, so first for part E, we're going to find f of 4. Okay, and again, that just means what is the actual function value when x is 4. So looking at the x value 4, this corresponds to the y value 4. So that's this point here. So we say, okay, f of 4 is equal to 4. So we're going to fill in the answer 4 here. All right, for part F, we're asked for the limit as x approaches 4 from the left now. Limit as x approaches 4 from the left. We don't look exactly at the x value 4, but near it, and coming in from the left. So if this is the left side of the value 4, kind of imagine drawing a line right through 4. We're going to follow along the graph going toward that line. So coming in from the left, we're headed towards this open dot here. And what is the y value for that open dot? Well, that open dot is located at the y value 6. So we would say that the limit as x approaches 4 from the left of f of x is equal to 6. Now how about the limit as x approaches 4 from the right? Actually, let me put another graph here. Okay, so coming in from the right towards the x value 4, once again, let's try and imagine, let's use blue this time. Okay, here's 4, but we're not concerned about what's happening at 4 anymore. We're concerned about what's happening near it, and specifically what's happening near it coming in from the right. So on the right side of the x value 4, we have this piece of the graph that we're going to follow along coming toward 4, and we see that that matches up with the y value 3. So the limit as x approaches 4 from the right is actually 3. So notice that we had previously found the limit from the left was equal to 6, and now we just found the limit from the right is equal to 3. In other words, the graph has a big jump in it. Coming in from the left, you get a very different y value than coming in from the right. So when we ask what's the overall limit as x approaches 4, the combination of from the left and from the right, well, that one doesn't exist. Because it would have to be equal on both sides to exist. So we would select the limit does not exist because the limit from the left does not equal the limit from the right. Okay, another type of, and again, please feel free to tell me if I need to repeat anything or you have any questions about anything. Or if you're watching the recording, you can always rewind. All right, so for this problem, we have a different kind of limit. This is a limit as x is approaching infinity. Actually, in this case, negative infinity, but either way, the same type of situation applies. The way that I'm going to explain evaluating limits at infinity is to say that if you're talking about either a polynomial or a rational expression, which this is because it has a fraction, the highest powers dominate. So the bottom of the denominator of the fraction only has one term, so that's the highest power term. But the numerator has two, so the only one that's going to apply is this one. So when you're talking about limits going toward infinity, you can actually ignore any other terms. So the limit we're looking for is going to be the same. It's not the same function, but the same limit as the limit of if it had just had those two terms, the largest degree in the top and the largest degree in the bottom. You have to include the square root, okay? So looking at this, one thing you want to check is since there is a square root, are we going to get negative values under the radical? And the answer is no, because when you square a negative, you get a positive, so that's not going to be an issue. Let's think about taking the square root. So think of this as the square root of 100 is 10. Now the square root of x squared, that's a little bit tricky. We would like to just write x, but keep in mind if x is negative, that would be a negative value, and we know that we're going to square it and make it positive, then take the square root. So we actually end up with the absolute value of x, not x itself. And then in the denominator we do have just x itself. Okay. All right, so this is going to be the same as 10 times the absolute value of x over x. I just want to separate that so that I think it makes it a little clearer to think about. The 10 is not affected when we plug in the negative infinity. Or larger and larger negative values. But the absolute value of x over x, this is going to have we can think about this separately. And like, for example, let's say as we are plugging in very large negative numbers for x, what would we get? So let's say x was equal to negative 100. Then what would you get for the absolute value of x over x? You would get 100 over negative 100. These would be opposites, so they would divide out to give you negative 1. Oh, and I'm doing something that I shouldn't do, which is I'm leaving off my limit. We need to limit, you need to write the limit every time, at every step, because it's the limits that are equal, not the actual expression. So to be precise, we would write this. Now, as we saw with negative 100, absolute value of x over x becomes negative 1, but that will work for any negative number, right? So as x heads toward negative infinity, this guy here is always going to be negative 1. So 10 times negative 1 is actually negative 10. Okay, so but the main idea here is that you want to just disregard any of the lower power terms in the top and lower power terms in the bottom. Now, the reason why this turned out to have a nice numerical answer as opposed to being infinity or negative infinity is because the denominator happened to have the same overall power or degree as the numerator in the end, right? Because once we take the square root of the squared, we end up with a power of 1, and we had a power of 1 in the bottom, so you're going to end up with a number. If we had had a power greater in the denominator, then the denominator would get very large much faster than the numerator, and you'd get tiny fractions and you'd get 0. And if we had had a greater power in the numerator, then we would have gone to positive or negative infinity because the numerator would have stolen the show from the denominator, basically. Okay, so it's going to be important that the degree, that you pay attention to the degrees of the, or powers of the x's, the variables in these limits. So I just want to make a little cheat sheet here. So it doesn't matter if it's plus or minus infinity. If you're taking a limit and you have x to a power p over x to a power q, okay, if p is greater than q, then your limit is going to be positive or negative infinity, depending on whether you end up with a quotient that is an even or an odd result. When you raise a negative number to an even power, you get a positive. If you raise a negative number to an odd power, you get a negative. If you have the limit as x approaches plus or minus infinity of x, well, I don't really need to write that again, the same limit, but when p is equal to q, like we had in this case, then that means you're going to get some finite number. And that number is actually the ratio of any coefficients. So let's say there was an a or a b, an a over b here, then the number that you would get is going to turn out to be a over b, plus or minus, depending on signs like we had up here. And then let's put plus or minus. And then if p happens to be less than q, then you're just going to get 0 because the denominator gets big much faster than the numerator. Okay, so limits to infinity, you need to be comfortable with these different scenarios. Okay. All right, so number 10 is different because number 10 is not a limit to infinity. Number 10 is a limit towards a finite value, but we are not given the graph this time. We're given the function, the algebraic expression that represents the function. So what we would like to be able to do, as we did in the problem where we had a square root earlier, is we'd like to just be able to plug in the value. But remember, you can only do that as long as you don't get imaginary numbers or undefined. So in this case, if I were to try to take the limit by plugging in the negative 11, oops, I don't need to write that at this moment. Negative 11 squared minus 121 over negative 11 plus 11 gives us 0 over 0, which is indeterminate. That we don't know what the limit is by looking at that. So we hope that what we can do is some algebraic simplification. So if it's a rational expression like this one, we'd like to try factoring and reducing if possible. So we're looking at the limit as x approaches negative 11, and in the top here, the numerator, we have x squared minus 121. So you might recognize that's a difference of squares because 121 is 11 squared. So the numerator factors into x minus 11 times x plus 11. And the denominator is not factorable. Just leave it alone. But we can reduce inside of a limit. So if the limit as x approaches negative 11 of x minus 11 times x plus 11 over x plus 11 is what we have, we can reduce that to the limit as x approaches negative 11 of x minus 11. Why? Because while this original function is undefined at negative 11, remember, limits are not about what happens at the point, but near it. So we can cancel out this, which tells us that it's undefined at that point, and we'll see what's happening near it. Now we have something we can plug into, so plug in, and you get negative 11 minus 11, which is negative 22, which is how they got their answer. So when you have a rational expression and you can reduce it, then plug in the limit value, you should go ahead and do that. Okay, let's talk about continuity, how you can tell looking at the equation of a function whether it's continuous or not. Okay, so an absolute value function is continuous everywhere. It doesn't have any holes or gaps, and we should remember that from maybe college algebra or algebra 2. Remember, the absolute value function looks like this. It's a nice continuous curve. It does have a sharp point, which is important when we start talking about derivatives, but it doesn't affect the continuity of the function. In other words, you can draw the picture of it without lifting your pen off the page, so you know that it's continuous everywhere. So what happens when you have to determine the continuity of something that looks like this? F of x equals absolute value of x squared plus x minus 6. Well, this is a composition of functions. We've plugged one function into another. But the function y equals absolute value of x, the outer function, that is continuous everywhere. And polynomial functions like x squared plus x minus 6, these are continuous everywhere. These are both continuous on the interval from negative infinity to infinity. So if you compose them, plug one into the other, it's still going to be continuous everywhere. So that's why they said that the function's continuous on the interval from negative infinity to infinity. Okay. So anytime you have a composition of functions and they're both continuous everywhere, you can conclude that. If one of them is discontinuous at a point, then you're going to have to pause and think about where that happens. Like, for example, if it's undefined somewhere. Okay, this is another example of a limit where it's an overall limit, not a limit from the left or the right. And we know that as long as we have, basically, if you can plug in algebraically and not get undefined, then you're probably in good shape. So in this case, we're talking about a polynomial function. Those are continuous everywhere, which makes finding the limit very easy. So you can just plug in the value. Okay. All right, let's talk about secant lines. So we're going to be focused a lot on secant lines and tangent lines in calculus. And the only difference between the two is secant lines, we're talking about a line that goes through 2 points on a curve, whereas a tangent line is a point that only touches the curve once. So finding the slopes of secant lines is a lot easier because the slope formula that you learned when you're finding the slopes of lines in a previous class, m equals y2 minus y1 over x2 minus x1, or if you write it in function notation, f of x2 minus f of x1 over x2 minus x1. This slope formula requires 2 points. And so that's why it's a lot simpler to find the slope of a secant line where it's going through 2 points on the curve than it is to find a tangent line. I'm not going to find all of the values here, but let's find a couple. So if we want to find the slope of the secant line on the interval from 1 to 2, what they're saying is that we have a function f. By the way, it's equal to 2x squared, and it goes through a point 1 something, and it goes through a point 2 something, and we're finding the slope in between. These are the x values. Okay, so f of x we're going to plug in to find y. So for example, when x is 1, 2 times 1 squared is just going to be 2 is the y value. When x is 2, we get 2 times 2 squared, so that's going to be 8. So the slope of the secant line is the slope, let me actually specify on what interval. So the slope on the interval from 1 to 2 is going to be y2 minus y1, 8 minus 2, over x2 minus x1, 2 minus 1, which is going to be 6. Okay, now let's look at the slope on the interval from 1.5 to 2. All right, so if we do 1.5 to 2, when we plug into the function f the x value 1.5, what are we going to get? Let's see. So we have 1.5 squared, and we're multiplying by 2. So the y value would be 4.5. So that's the point at one end of the interval. At the other end, we already know that we have 2, 8. So the slope between 1.5 and 2 is going to be, oops, I wrote infinity instead of 8. There we go. The slope's going to be 8 minus 4.5 over 2 minus 1.5. Okay, and let's see, what is that going to be equal to? 3.5 divided by 0.5 is 7. Okay, and then that's 7. Let's do one more. I'm going to skip down here. You should see that there's a pattern, because as we get closer and closer to 2, we're getting closer and closer to the slope of the tangent line. So what if we put in 1.999 to our function? What do we get? 1.999 squared times 2 equals 7.992002. Okay, so the slope between the 2 points, 1.999 and 2, we're going to have the y value 7.992002 minus the y value 8 divided by, and then we're going to have 2. Oh, did I do that backwards? I did. I was doing it the other way around, so to be consistent, I'm going to use the 8.2 as my x1, y1. So it's going to be 8 minus 7.992002, and then 2 minus 1.999. So let's see, that's going to be 7.998. Okay, so this is very close to 8, and I bet you if I continued with this chart down to 1.999999, it would get even closer to 8. So the slope of the tangent line, which goes through only the point 2, oh, maybe not. Maybe I did something wrong. Let's see. Oh no, that's right. Is going to get very, very close to 8. Okay. Now there's a better way to find the slope of the tangent line, which is using derivatives, but when we first are discussing tangent lines, whenever we are talking about a graph, like let's say this is our graph, this is the x value too. So we consider slopes of secant lines first because we can know the slope between 2 points easier than the slope at a single point. But if you keep taking slopes of secant lines that are through points closer and closer to 2, you're going to get very, very close to the slope of the tangent line that only touches the graph at 2. And that's what we were doing in that chart. Oh, good morning, Sharon. I'm glad you're able to log in. Please feel free to type in any questions that you might have, or if you need me to repeat something, let me know. All right. All right, so we already discussed limits to infinity and negative infinity. And here's another example. Let me scroll back up. Remember, you have access to this in your OneNote file. But when we were discussing limits to infinity a minute ago, where did it go? Here we go. We said that when we have a ratio of x to a power over x to a power, that when the degree in the top is bigger than the degree in the bottom, we get plus or minus infinity. If they're equal, we get the coefficient plus or minus the coefficient, and then if the numerator has a less degree than the denominator, then we get 0. All right, so we're going to apply that same idea down here. But we're going to talk about it in the context of what it means about the graph. So if you take a limit to infinity, what you're really talking about is the end behavior of the function. So just as a generic example, something that we're all very familiar with is the graph of y equals x squared. So let's say that this is the function f of x equals x squared. If I asked you what's the limit as x approaches positive infinity of x squared, I'm talking about the end behavior of this function as it goes out to positive infinity. And that's this side. Notice that it's going upward, right? It's going up, which means the y values are going toward positive infinity as the x values are going towards positive infinity. As we go this way, the x values are going towards positive infinity, but also, since it's going upward, the y values are too, so you would get positive infinity. Now the limit as x approaches negative infinity is talking about the end behavior of the graph on the other side. So this was the positive side here. On the other side, going towards negative infinity, we're talking about this guy over here, following along as x goes out towards negative infinity. What's happening to the y value? The y values are still going upward to positive infinity. So this would still be positive infinity even though there's a negative down here. On the other hand, if you were looking at a graph that pointed downward like x cubed, the y values would be going toward negative infinity. So you have to think about, when you think about the limit as x approaches positive or negative infinity, you can think about the end behavior of the graph. So let's go down to this guy here. All right, So it says to analyze the limits to positive and negative infinity of this function x to the fourth minus 225 over x squared minus 15. All right, so when you're finding a limit to infinity, remember the highest powers dominate. So this limit is the same as the limit as x approaches infinity of x to the fourth over x squared. And so this is a situation where there's a higher degree in the numerator. You can go by the rule that I gave you that says that it's going to go to positive or negative infinity, but how do you figure out which one? Well, think about it this way. What is x to the fourth divided by x squared? That's just x squared, right? And you're plugging a positive number into x squared, so you're going to get a positive number. So this goes to positive infinity. So what this is telling you is x going to positive infinity is talking about the right side of the function, and we just saw that the y values are going to positive infinity. So in other words, the end of the graph is going upwards on the right. All right, so the answer to that part is positive infinity, but I want you to think about what it tells you about the graph. It's going upwards on the right. Okay, now the next one, we're going to work the same way. And when you're taking limits to infinity, you don't even have to pay any attention to any of the terms except for the highest powers. They dominate. So this is going to be the limit as x approaches negative infinity of x to the fourth over x squared, which we know is the same as the limit as x goes to negative infinity of just x squared. So then you think, what happens when you plug large negative numbers into x squared? Well, any number squared is positive, so you're still going to get positive infinity. So that means that the y values are still going up on the left side of the graph. Okay, so regardless of what's happening in the middle of the graph might be all squiggly in the middle. It might have vertical asymptotes somewhere in there, which this one actually will, so it might look like this or whatever. But on the ends, we know that the end behavior of the graph is going up on the right and up on the left. And what horizontal asymptotes are is just a way of describing of what's happening on the ends. And in this case, since it's going upwards without bound on the ends, there is no limiting number, so it has no horizontal asymptotes. Okay, now let's talk about vertical asymptotes. Now remember, the function that we're looking at is x to the fourth minus 225 over x squared minus 15. Let me write that as a function. Let's see. F of x equals x squared minus 225 over x squared minus 15. No, x to the fourth, excuse me, minus 225. Okay, so when we're talking about vertical asymptotes, we're talking about where the denominator is 0. So what values of x would make this denominator equal 0? So if we solved that equation, x squared minus 15 equals 0, we would move the 15 over, we'd get x squared equals 15. We would use the square root property and we'd see x equals plus or minus the square root of 15. All right, this is looking really messy, so I'm going to come over here and talk about it. All right, so you set the denominator equal to 0. Now you might think that that must mean that we have vertical asymptotes at x equals plus or minus the square root of 15. But actually, it's possible that we don't. There's one of two things that can happen. If this were the function just 1 over x squared minus 15, that would definitely have vertical asymptotes. But in this case, it's possible that instead of a vertical asymptote, you just have a hole in the graph. And the way that you tell which is which is if the rational, when you have a rational function like these, rational function just means they're fractions, you check to see if it can be reduced. So all we really know for sure at this point is that f is undefined at these values, right? So if you try to plug square root of 15 into the function, yes, you get undefined. But is it undefined like you have an asymptote? Or is it undefined like you have a hole in the graph? That's the question that we need to figure out. So the only way you can have an asymptote is if you can't reduce the fraction to get rid of the factor that gave you the undefined value. So let's see if we can reduce this to cancel out that denominator. So notice that the numerator is a difference of squares. It's x squared squared minus 15 squared. Okay, so a difference of squares factors into what are called conjugates, the plus and the minus in the middle. So we can factor that into x squared minus 15 times x squared plus 15. And in the denominator, we have x squared minus 15. So in fact, the x squared minus 15, which leads to the undefined x values, is it cancels out. So we could say that f of x is actually equal to x squared plus 15 as long as x is not plus or minus the square root of 15, because it's undefined at those values. So in fact, this is a case where we have holes in the graph, not vertical asymptotes. Okay, so just keep in mind, yes, you find vertical asymptotes by setting the denominator equal to 0, but it's possible they're not actually vertical asymptotes, they're just holes in the graph. I also want to show you, I'm going to pull up the website desmos.com and show you what this graph looks like. Let me see. This is a great graphing website. All right, so if we want x to the 4th power minus 225 divided by x to the 2nd power minus 15, and I'm going to call this one f of x. Okay, so shrink a little bit here, step back. All right, so in fact, this looks like a parabola, right? And that's consistent with what we saw. We said that this function actually looks like the parabola x squared plus 15. It's just that it's undefined at plus or minus the square root of 15. Now you can't see that on the desmos.com graph. Where did I put my graph here? Okay. Why? Because there's just one value. I'm going to spread out my graph here a little bit more. Okay, there's just one value, so I'm going to put in a line at the square root of 15 negative square root of 15. Okay, so at that line, the function is undefined, but it's just undefined at a tiny point, right? It has no width, so you can't actually see it on here. If I was drawing it on my paper, I would represent it with a an open dot, but since it's on since the computer is graphing it, it's not including that open dot in the graph. But you can definitely see there's no asymptote that the function is following along. It just looks like a regular old parabola if we didn't know that there's a hole in it. Okay. All right. Okay, one of the skills from trigonometry that trips people up, and it does come up in calculus problems in a variety of contexts, is solving a trig equation. So I want to look at solving this trig equation with you, and remember, you can let me know if you have any questions, type them into the chat bar, or let me know if I need to repeat anything or work a different problem. Okay, so I'm going to solve this one where we have the sine. So let's pretend for a moment that we were solving the equation sine of theta equals square root of 3 over 2, where theta is between 0 and 2 pi. All right, you should recognize square root of 3 over 2 is a sine of a special angle, one of our angles that are multiples of 30, 45, or 60 degrees or 90 degrees, those special angles that are on our unit circle. All right, so let's think about our unit circle. In order for an angle theta to have a sine of root 3 over 2, a positive sine value, we have to either be in the first or second quadrant where the sine values are positive. Sine is opposite over hypotenuse. And so since the sine is, I always think of it this way, root 3 over 2 is bigger than 1/2. So the sine of theta being root 3 over 2 means you're talking about 60 degrees or pi over 3. So this angle here would be pi over 3. Whereas if it had been 1/2, we would have had an angle of pi over 6, a smaller angle. All right, and then the reference angle on the other side is also pi over 3. But the angle value that we would solve the equation with would be this one here, which is pi minus pi over 3, or 2 pi over 3. So if we were just solving this sine of theta equals root 3 over 2 for theta on the interval from 0 to 2 pi, we would just have theta equals pi over 3, 2 pi over 3. There would be no more angles between 0 and 2 pi that would work. Okay, but this problem that we're solving is a bit different because they're talking about the sine of 3x, where x, not 3x, but x, is between 0 and 2 pi. So whenever you have a multiple of your argument angle, or a multiple of an angle x in your argument, you're going to have to adjust the angles you're looking at on the unit circle a little bit by either going around fewer or more times. So the way that I like to think about it is if x is between 0 and 2 pi, if we know that our angle x that we're looking for is between 0 and 2 pi, then what would 3x, where would 3x have to be? The angle 3x would have to be somewhere between 0 and 6 pi, right? It's 3 times as big. And you can get that by multiplying 3 times each part here. And you know that 3x is between 0 and 6 pi. So if I change the problem that I just worked to say the sine of 3x equals root 3 over 2, and I'm looking for 3x to be somewhere between 0 and 6 pi, I'm going to get more answers than I did a minute ago. My angle 3x could be still pi over 3 or 2 pi over 3, but we're not stopping when we get to 2 pi. We're going to keep going. So each time we go around, we're adding 2 pi, correct? So it's also possible for this to be pi over 3 plus 2 pi. Well, pi over 3 plus 2 pi is the same as pi over 3 plus 6 pi over 3. So that would give us 7 pi over 3. It would still be an angle ending at this terminating side of the angle here, but it measures pi over 3 plus 2 pi. So we get an additional angle. The next one is 2 pi past 2 pi over 3. So we would have our 2 pi over 3 we had before. We need to add 2 pi to it. Or in other words, add 6 pi over 3. So that's going to give you 8 pi over 3 to get around to this angle here. 8 pi over 3. Okay, so then if we go around that, we've gone around one more time, we've hit 4 pi, but we still can go around one more time again. So take the 7 pi over 3 and the 8 pi over 3 that you just found and add 2 pi to that again, or in other words, add 6 pi over 3. So 7 pi over 3 plus 6 pi over 3 is going to be 13 pi over 3. So that's another answer. And then 8 pi over 3 plus 6 pi over 3 is going to be 14 pi over 3. Okay, but all of these values that we just found here are measures of 3x, and we're looking for x. So what can we do to find x? Well, just like when you solve any equation, if 3 is being multiplied by x, we reverse that by dividing by 3. All right, so dividing each one of those angles by 3, you're going to have, instead of pi over 3, you're going to have pi over 9. Instead of 2 pi over 3, you're going to have 2 pi over 9, and so on. So it looks like we are going to have C is going to be the solution here, right? Because instead of 3x equals pi over 3, we have x equals pi over 9, and so on. Okay, is there any part of that problem you'd like me to repeat, or? Are we good to go? Okay, so just want to make sure everybody's clear. To get from here to here, you divide by 3. All right. Okay, let's look at this example of continuity. So they are giving us a function f of x equals e to the x over 1 minus e to the 6x. So when we're asked to determine the intervals on which the function is continuous, you have to know that this function is constructed out of other functions. It's constructed out of e to the x and e to the 6x, which are both continuous everywhere. So you need to know that there's those two functions that in and of themselves are not going to cause any discontinuities. But whenever you have, oh, I see a question. On the test, will we have a unit circle to look at, or do you need to memorize? You need to memorize your unit circle, yeah. You need to be able to reconstruct it from memory, for sure. Okay, there are some YouTube videos with some nice tips on learning the unit circle. If you just run a search on memorizing unit circle, you'll see a bunch of videos there. Good question. Okay. All right, so as far as the continuity of this function goes, the only thing that can cause a problem then is that it has a denominator, and we know that if we have a 0 in the denominator, that can cause a discontinuity. So when you're asked on which intervals the function's continuous, we're going to find any sources of discontinuity by setting the denominator equal to 0. 1 minus e to the 6x equals 0. Okay? If there was a square root, then we know there could be a discontinuity when at whatever point where the number under the square root becomes a negative. In other words, you can only have continuity on intervals where the number or expression under the radical is positive if it's an even root. If it's an odd root, you don't have to worry about that at all. So roots and denominators are two of the times that you have to watch out for discontinuities. Natural logs and logs also, the argument can only be positive. But e to the x, e to the 6x, those are continuous everywhere. That's not going to cause a problem. All right, so solving this, though, we would have 1 is equal to e to the 6x, which is the same thing. If we take the natural log of both sides, would be one way to solve it. We get the natural log of 1 equals the natural log of e to the 6x. Now remember, natural log is log base e, so this is literally saying what power do you raise e to get e to the 6x. So the base cancels out with the log. Natural log of 1, what power do you raise e to get 1? The 0 power. And so x is equal to 0 divided by 6, or 0, is the only place where we're going to have a discontinuity. So if on our number line we leave out the value 0, we have the interval from negative infinity to 0 is continuous, and the interval from 0 to infinity is continuous. So that's what you would type in here. Okay. All right, so then it's not any wonder that we are interested to see what happens as far as the limit of the function as x approaches 0 from the left and from the right. We're often interested in limits as x approaches points of discontinuity, because we know what's happening at that function value. We have, in this case, a vertical asymptote, but we don't know what's happening maybe near it, and we would like to analyze that. All right, so let's talk about the limit as x approaches 0 from the left of f of x. First of all, whenever you have to find a limit from the left or a limit from the right going toward a particular value like 0, what I like to do is to think about, can I just find the overall limit by plugging in? Remember, we like to evaluate limits by just plugging in if we can. So let's see if that works or not. So if I were to just try plugging into e to the x over 1 minus e to the 6x, We know that we can't plug in just 0 here because that would give us 1 minus 1 in the denominator, which is the reason why we have a discontinuity at 0. But is there some way that we can simplify this? Maybe, maybe not. Let's see. So, oh, I was thinking wrong for a second. Hold on, give me a moment. No, I don't think so. I don't think there's a way we can plug in. So I can't think of a way to algebraically rearrange this. I might be missing it. Let me think. Maybe. But instead, if you're not sure, what you can also do is you can plot a few points close to, not plot, but evaluate a few function values close to 0 on the left and on the right. So let's go ahead and try and think about each one separately. So we're going to look from the left. So when I say from the left, I'm talking about values very close to 0, but on the negative side. So we might be plugging in, for example, negative 0.1, negative 0.01, negative 0.001, just to get an idea of what's happening here. So these are the x values, and they're getting closer to 0. And then our y values, or f of x values, I guess I should say, we get by plugging into this expression. So let's pull up our calculator. By the way, you definitely want to use a calculator on the test. Okay. So we're going to have to go to our, let's see, are we on scientific? I think we are. Okay. Here we go. All right, so we're going to do plugging in negative 0.1 right now. We're going to do e to that power, so 0.1 negative e to that power. That gives us the numerator. We're going to divide that by parenthesis. We're going to have 1 minus, and then parenthesis again, 6 times negative 0.1. Close parenthesis, equals, and we get 0.565, so about, well, let's just put 0.566. Okay. And then if we do negative 0.01, check my arithmetic here too as I go. Plug this in if you have your calculator in front of you to make sure I don't make a mistake here. So we're going to have negative 0.01, and we're going to have e to that power, and then we're going to divide that by parenthesis 1 minus, and then in parenthesis I have no. One minus, and then we're going to have 0.01 negative Oh, did I forget to put the 6 in before? I think I did. Not sure. Times 6. I'm not liking this calculator here. I want to use my calculator. Hold on. Okay, so we have I'm still here. Sorry, guys. I'm just plugging into the calculator. I'm redoing the first part because I think that I forgot to plug the 6 in. So this is going to be e to the negative 0.1 over 1 minus e to the negative 0.6. Yeah, I think that actually comes out to negative 1.005. If you could check for me. And then the next one is going to be e to the negative 0.01 over 1 minus e to the negative 0.06. And that comes out to be 17. Not sure why that would have been negative though. Let me see, let me just double check that again, sorry. 0.1 negative e to the divided by parentheses 1 minus, and then we have 0.6 negative e to the close parentheses. Oh yeah, that should have been positive 2.05. I'm not sure why I got that. Okay. And then we're going to go on down here and we're going to have e to the negative 0.001 over 1 minus e to the negative 0.006. Okay, and that's going to be 167. All right, so you can see that there's a trend here. If you keep plugging in, you should see that you get larger and larger positive numbers. So the limit as x approaches 0 from the left of this expression, if this is yielding larger and larger positive numbers, then it doesn't have a bound, so it's going to be increasing without bound, or in other words going to positive infinity. Okay, and then for the next part you're going to do the same thing, except you're just going to be plugging in the positive versions of these, and what you should find is that you're going to get negative values, large negative values. And so you can do the limits to infinity, the limits that turn out to be infinity when you're looking at a limit from the left and a limit from the right of a point of discontinuity in a rational function. You can plug in some values and see if it's going towards positive or negative infinity. Okay. You can also try graphing. If you're at home and you can't use a graphing calculator on the exam, you would have to use a table like this, but if you just wanted to check it at home, you could also try graphing this function and seeing how it behaves close to 0. Okay. Right. Unit circles, we already talked about that. It's a review of graphs of logs. Okay, let's talk about simplifying a difference quotient. This is going to be the last thing that we look at today. So simplifying a difference quotient is important in calculus. All a difference quotient really is a formula for slope. If you notice, this is a y value here, the y value when x is x, and then this is a y value when x is a. So you have a difference in y's over a difference in x's. The limit of that difference quotient is going to give us the slope of the tangent line, but first we have to be able to actually just deal with this expression and how to simplify it. So let's practice. So you might have also seen the difference quotient, by the way, written as f of x plus h minus f of x over h. And the only difference here is that instead of using an a as one of the x values, they've used an x plus h as one of the x values. And that way in the denominator you get x plus h minus x, which simplifies to h. So they look different, but in fact they're both just a different way of writing a slope formula in function notation. But anyway, we're going to use this one for this problem. So we're going to have f of x in our numerator, which is given to us to be x cubed minus 15x. And then we're going to have f of a in our numerator, and that's just a cubed minus 15a. So in the numerator, we're going to have x cubed minus 15x, this is this expression here, substituted in, and then a cubed minus 15a substituted in, and then this is all going to be over x minus a. Okay, and we would like to simplify that. So the question is, how can we simplify that? So one way is to use grouping. And in fact, we already have the reason why I'm suggesting using grouping is because that's a method of factoring that can be used when you have 4 terms in a polynomial. And if you look right here in this numerator, we have a 4-term polynomial. It doesn't have anything in common to all 4 of the terms, but pairs of terms have something in common. So you might recall that from algebra. So for example, here in the x cubed minus 15x, I could factor out an x, leaving x squared minus 15 behind. And then in the other one, I could factor out an a, leaving a squared minus 15 behind. Oh, that's not going to help because we're going to have a different, oh no, yeah, well, no, actually I guess it won't. All right, let's try a different approach. I would like to get a factor of x minus a so that I can cancel it out. And I thought it was going to work because I get an x minus a here, but notice that these two are not the same, so that's not going to work. So another thing you can do is to try rearranging the numerator a little bit and grouping differently. So let's see what we can do. So first, distribute your negative. You have x cubed minus 15x minus a cubed plus 15a over x minus a. Okay, now I'm going to rearrange this. I'm going to put the x cubed and the a cubed together, and I'm going to put the negative 15x and the positive 15a together. And let's see if grouping will work that way. All right, so x cubed minus a cubed fits a pattern. It's a difference of cubes. I just want to remind you the way difference of cubes works. So if you have a cubed minus b cubed, it factors into something with an a and a b, an a squared, an ab, and a b squared. To remember which signs go in here, you look at this sign here. It's going to be the same sign, the opposite sign, and then always positive. It spells soap. So that's going to be the same sign would be negative, the opposite sign would be positive, and then this one's always positive. So in this case, we're factoring x cubed minus a cubed. That's going to factor into x minus a times x squared plus ax plus a squared. Okay, that's all just this part here that I've factored. All right, and then over here, the other two, we're going to factor out a negative 15. So that's going to be negative 15 times, and then that leaves behind a positive x and a negative a. So that way, I do have a factor of x minus a in each of these two big terms that I've created here. Okay, so then dividing x minus a out of all three parts, we're left with x squared plus ax plus a squared minus 15. It all divides out and cancels. Okay. All right, so that's an example of simplifying a difference quotient without the actual taking the limit, which gives us the derivative. All right, so I hope you found our chat helpful. I'm going to have to stop now. I have another chat starting at noon. Are there any questions before we log off? So this practice test that I printed out in your OneNote folder, it has it's a printed out version of the practice test that you have in my math lab, and it has answers to the questions in here. Of course, the one in my math lab will regenerate different number values, but it'll be the same basic types of questions. So what you could do to improve your score on your practice test, instead of taking it multiple times online, you could work it out on paper using this OneNote file, and then go in and take the practice test for test 1 in my math lab, and hopefully the first time you do it you'll score higher that way. And then don't be shy about sending me your questions. Once you have taken the practice test, when you go to review the test in the grade book in my math lab, you can review it by clicking on the word review in the grade book. And when you do that, you have the option of sending me an Ask My Instructor question. So if you have a question about a particular item, it'll email me an exact copy of that item. So I hope you found the chat helpful. If you did, please give it a thumbs up to help the other students to find it. I am going to be posting a link to the recorded version as well. And my students, you can post a comment on the recorded version if you missed the live chat, and you can still get some bonus points. Alright guys, don't be strangers. I know it's an online class, but I'm here to help you and I want you to be successful. Take care.